Tonight, we're going to explore something that sounds like science fiction, but is actually one of the most sobering truths about humanity's future. We dream of spreading across the cosmos, colonizing distant galaxies, becoming a truly intergalactic civilization. But here's the reality that physicists and astronomers rarely talk about in simple terms. We might be trapped, not by technology or lack of willpower, but by the fundamental nature of the universe itself. By the end of tonight, you're going to understand why the Milky Way might be the only galaxy humanity will ever call home, and why crossing the void to another galaxy might be physically impossible, no matter how advanced we become. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what most people imagine when they think about space travel. You've seen it in countless movies and TV shows. Spaceships jumping between star systems, crossing vast distances in moments, exploring different galaxies as easily as we explore different countries on Earth. It looks effortless. The Enterprise warps to distant worlds. The Millennium Falcon makes the jump to hyperspace. Interstellar travelers hibernate for years and wake up in another galaxy. These stories have shaped how we think about humanity's cosmic future. We assume that given enough time and technological advancement, we'll figure out how to travel between galaxies just like we figured out how to cross oceans. It's just a matter of engineering, right? Build faster ships, develop better engines, solve the propulsion problem, and the galaxy, any galaxy, becomes accessible. But this assumption misses something fundamental about the universe we live in, something that no amount of technological advancement can overcome. The problem isn't just that intergalactic distances are large. The problem is that the universe itself is working against us, actively pushing those distances larger every single moment. And it's getting worse. To understand why we might be trapped in the Milky Way, you need to understand three things. First, how far away other galaxies actually are. Second, how fast the universe is expanding. And third, why that expansion creates a barrier that no conventional spacecraft, no matter how fast, can ever cross. Let's tackle these one at a time, starting with distance. The Milky Way is our home galaxy. It contains somewhere between 200 billion and 400 billion stars. Our Sun is one of them, located about 26,000 light-years from the galactic center, out in one of the spiral arms. The entire galaxy stretches about 100,000 light-years across. That's already an almost incomprehensible distance. Light, traveling at 300,000 kilometers per second, takes 100,000 years to cross from one side to the other. If you could somehow travel at the speed of light, which physics says you can't, it would still take you 100,000 years to traverse our galaxy. But let's say we solve every engineering challenge. Let's say we build ships that can travel at a significant fraction of light speed. 10%, maybe even 50%. That would make crossing our own galaxy possible within a human timescale, at least from the perspective of travelers experiencing time dilation. Getting to another star system becomes feasible. Even crossing from one side of the Milky Way to the other becomes theoretically possible. You could imagine a slow expansion across our galaxy over thousands or millions of years, establishing outposts, spreading from star to star. This is the dream of becoming a galactic civilization. And it's actually somewhat plausible, given enough time and advancement. But here's where the problem starts. The nearest major galaxy to us is Andromeda. You can actually see it with the naked eye on a dark night as a faint smudge in the constellation Andromeda. It's the most distant object visible to the unaided human eye. Andromeda is 2.5 million light-years away. That's 2.5 million years at the speed of light. 2.5 million light-years is 25 times farther than the width of our entire galaxy. To put this in perspective, imagine you're standing in New York City. The Milky Way is like walking from New York to Los Angeles, coast to coast across the United States. It's far. It takes planning and effort. The distance to Andromeda is like walking that same coast-to-coast distance 25 times. Back and forth, over and over. Except it's not just 25 times. Because you're not walking through static space. The universe is expanding. And this is where everything changes. In 1929, Edwin Hubble made a discovery that revolutionized our understanding of the universe. He observed that distant galaxies are moving away from us. All of them, in every direction. And the farther away they are, the faster they're receding. This wasn't because galaxies are moving through space away from us, like objects flying apart from an explosion. Instead, space itself is expanding. The fabric of the universe is stretching, and galaxies are carried along with it like raisins in rising bread dough. As the dough expands, the raisins get farther apart, not because they're moving through the dough, but because the dough itself is expanding. Hubble quantified this expansion with what's now called the Hubble constant. The current best measurement puts it at about 70 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light-years. What this means is, for every 3.26 million light-years of distance, space is expanding fast enough to make objects recede from each other at 70 kilometers per second. Andromeda is about 2.5 million light-years away, roughly 3/4 of a megaparsec. So you might think space is expanding between us and Andromeda at about 52 kilometers per second. Except Andromeda is actually moving toward us. It's one of the very few galaxies showing a blue shift instead of a red shift, meaning it's approaching rather than receding. This is because Andromeda and the Milky Way are gravitationally bound to each other. We're part of the same local group of galaxies, and our mutual gravity is strong enough to overcome the expansion of space at this distance. We're falling toward each other, and in about 4 billion years, we'll collide and merge. But Andromeda is a special case. It's the only major galaxy close enough that gravity overcomes expansion. Look beyond our local group, beyond the handful of nearby dwarf galaxies that orbit us, and everything else is receding. And the farther away you look, the faster the recession. The Virgo cluster, a large collection of galaxies about 53 million light-years away, is receding at about 1,200 kilometers per second. That's about 0.4% the speed of light. The Coma cluster, about 300 million light-years away, recedes at about 7,000 kilometers per second, over 2% light speed. Go far enough, and galaxies are receding faster than light. This sounds impossible. Einstein's theory of relativity says nothing can move through space faster than light. But that restriction applies to motion through space. It doesn't apply to the expansion of space itself. Space can expand at any rate. There's no speed limit on the stretching of the universe. Objects embedded in that expanding space can be carried apart faster than light. Not because they're moving through space faster than light, but because the space between them is growing. This has a profound implication. There's a distance beyond which galaxies are receding from us faster than light. This distance is called the Hubble radius, and it's currently about 14 billion light-years. Any galaxy farther than this is receding faster than light. And here's the critical point. If a galaxy is receding faster than light, you can never reach it, no matter how fast you travel. Even if you could travel at the speed of light, you'd be like someone running on a treadmill that's moving backward faster than they can run forward. You'd make no progress. In fact, you'd fall farther behind. But wait, you might think. 14 billion light-years is really far. Most galaxies are closer than that. Why does this matter for intergalactic travel? Because the universe's expansion is accelerating. This is one of the most important discoveries in modern cosmology, made in the late 1990s. Astronomers studying distant supernovae expected to find that the universe's expansion was slowing down, decelerated by gravity, pulling everything back together. Instead, they found the opposite. The expansion is speeding up. Something is pushing galaxies apart faster and faster over time. We call this something dark energy, but we don't really know what it is. We just know it's there because we can measure its effects. Dark energy makes up about 68% of the total energy content of the universe. It's the dominant component, and it's causing the expansion to accelerate. What this means is that the Hubble radius, the distance at which recession velocity equals light speed, is not fixed. As the universe ages and expansion accelerates, more and more galaxies cross this threshold. Galaxies that are currently receding slower than light will eventually be receding faster than light. And once they cross that line, they become unreachable. Forever. Not just unreachable for current technology. Not just unreachable for civilizations that can only travel at 10% or 50% light speed. Unreachable even for hypothetical civilizations that somehow master traveling at light speed itself. Let's make this concrete with an example. Pick a galaxy that's currently receding at, say, 50% the speed of light. That's slower than light. So in principle, if you could travel fast enough, you might catch up to it. Build a ship that travels at 75% light speed, and you'd be closing the gap. But here's the problem. While you're traveling toward that galaxy, the universe keeps expanding, and the expansion is accelerating. By the time you cover some of the distance, the galaxy has receded farther than it was when you started. And worse, the rate at which it's receding has increased. You're chasing a target that's not just moving away, but accelerating away from you. For most galaxies beyond our local group, you can't catch up even at light speed. The math doesn't work. Space is being created between you and your destination faster than you can cross it. It's like trying to reach the end of a hallway that's stretching faster than you can run. Even if you run at maximum speed, the hallway gets longer faster than you can cover the distance. Now, there's a common response to this. People say, what about wormholes or warp drives or other exotic physics? Surely, if we can bend space-time in the right way, we can bypass these limitations. And it's true that general relativity allows for certain theoretical solutions that would permit faster-than-light travel. Wormholes are tunnels through space-time that connect distant regions. If you could create and stabilize a wormhole, you could step through and emerge light-years away, covering vast distances in moments. The Alcubierre drive is another theoretical concept where you create a bubble of space-time around your ship. The bubble contracts space in front of you and expands it behind you, allowing you to move faster than light relative to distant objects without actually moving through space faster than light locally. These ideas are mathematically consistent with general relativity. The equations work. But there's a catch. Actually, several catches. First, creating a wormhole or warp bubble requires exotic matter, specifically matter with negative mass or negative energy density. We've never observed such matter. It might not exist at all. Quantum field theory allows for temporary, tiny regions of negative energy density under very specific conditions. But scaling that up to macroscopic amounts needed for a wormhole or warp drive is purely speculative. We have no idea if it's possible. Second, even if you could create exotic matter, the amounts required are staggering. Early calculations for the Alcubierre drive suggested you'd need negative energy equivalent to the total mass energy of Jupiter. Later refinements reduced this somewhat, but it's still an absurd amount of energy and exotic matter. We're talking about energy scales, far beyond anything humanity can currently manipulate. Third, wormholes are unstable. According to general relativity, a wormhole would collapse almost instantly unless you thread it with exotic matter to hold it open. And even then, anything passing through would likely destabilize it. You might send a probe through, but the wormhole could collapse before you got data back or before a second probe could follow. Fourth, causality violations. Some solutions that allow faster-than-light travel also allow time travel into the past. This creates potential paradoxes. Many physicists believe that unknown laws of physics we haven't discovered yet will forbid these solutions, precisely because they lead to paradoxes. In other words, there might be a cosmic censorship principle that prevents these loopholes from actually working. And finally, even if you solve all these problems, there's still the practical issue. You need to get your exotic matter, wormhole generator, or warp drive to the destination first. If you want to create a wormhole between the Milky Way and Andromeda, you need to have infrastructure at both ends. That means someone has to make the trip conventionally first to set up the other end. And if you can't make the conventional trip because the expansion of space prevents it, you can't set up the wormhole. So, exotic physics doesn't necessarily save you. It might allow faster travel within a region you can already reach conventionally, but it doesn't help you reach regions that are fundamentally inaccessible due to cosmological expansion. Let's talk about what this means practically. Our local group of galaxies contains about 80 known galaxies. Most are dwarf galaxies, much smaller than the Milky Way. The major members are the Milky Way, Andromeda, and the Triangulum galaxy. These galaxies are all gravitationally bound together. They're close enough and massive enough that their mutual gravity holds them together despite the expansion of space. Over the next several billion years, they'll merge into a single large galaxy. This local group occupies a region about 10 million light-years across. Everything within this region is potentially reachable. Difficult, certainly. A trip to Andromeda would take millions of years, even at a substantial fraction of light speed. But it's not prohibited by the expansion of the universe. Gravity holds our local group together. Beyond the local group, though, things change. The Virgo cluster is the nearest large cluster of galaxies, about 53 million light-years away. It contains over 1,000 galaxies and is part of the larger Virgo supercluster, which our local group is also part of. But despite being in the same supercluster, we're not gravitationally bound to the Virgo cluster. The expansion of space is stronger than gravity at this distance. Virgo is receding from us, and that recession is accelerating. Current calculations suggest that Virgo is already beyond our cosmological event horizon. This is the boundary beyond which objects are receding faster than light. We can still see Virgo. Light that left Virgo millions of years ago is reaching us now. But we can never reach Virgo. Even traveling at light speed, we'd fall farther behind. And it gets worse. As the universe ages and dark energy continues to accelerate expansion, the cosmological event horizon will shrink. Galaxies that are currently within reach will eventually cross the boundary and become unreachable. Billions of years from now, only our local group will remain accessible. Everything else will have receded beyond the horizon. Eventually, the universe's expansion will have carried all other galaxy groups so far away and so fast that their light will no longer reach us. Future astronomers living billions of years from now will look out at the sky and see nothing but their own merged local group. All evidence of the larger universe will have disappeared beyond the observable horizon. They'll live in an island universe, cosmologically isolated, with no way to know that billions of other galaxies exist beyond the darkness. This is called the Big Rip scenario in some versions of cosmological evolution, or heat death in others, depending on the nature of dark energy. But the end point is the same: eventual, complete isolation. So here's the reality. Humanity, if it survives, might spread throughout the Milky Way. We might colonize thousands or millions of star systems. We might build a true galactic civilization that lasts billions of years. When the Milky Way merges with Andromeda, we might spread into that larger, merged galaxy, colonizing its stars as well. We might even reach some of the dwarf galaxies in our local group. But beyond that, the door is closed. The Virgo cluster, the Fornax cluster, the Coma cluster, all the galaxy clusters and superclusters beyond our local group are unreachable. Not unreachable because we lack the technology. Not unreachable because the trip would take too long. Unreachable because the universe itself makes them inaccessible. The space between us and them is expanding faster than we can cross it. This is a hard limit, imposed by cosmology. No amount of technological advancement can overcome it. You can't engineer your way around the accelerating expansion of the universe. Now, some people find this depressing. The idea that we're cosmologically trapped, that the universe is vast beyond imagination, but most of it is forever out of reach. It feels limiting. Like the universe is taunting us, showing us trillions of galaxies we can observe but never visit. But there's another way to look at it. Our local group, when fully merged, will contain over 1 trillion stars. That's 1 trillion suns, each potentially hosting planets, moons, asteroid belts. Each one a potential home for life or for future human colonies. 1 trillion stars is an almost incomprehensible number of destinations. At one new star system per year, it would take 1 trillion years to visit them all. The current age of the universe is only about 14 billion years. You could sustain a thriving, expanding civilization for millions or billions of years, just exploring our local group. And unlike trying to reach distant galaxy clusters, exploring our local group is actually possible. Difficult, yes. It would require technology we don't have yet. But it's not prohibited by physics. It's engineering, not impossibility. So in a sense, we're trapped in a very large cage. A cage containing 1 trillion stars and countless worlds. That's not nothing. That's actually extraordinary. The question is whether humanity will survive long enough and advance far enough to even begin exploring our cosmic neighborhood. That's not guaranteed. We might go extinct before we leave our own solar system. We might never develop the technology for interstellar travel. We might destroy ourselves through war, climate, disaster, or some other catastrophe. Those are real possibilities. But if we do survive, if we do advance, if we do spread out into space, the Milky Way and our local group offer more than enough room for humanity's future. You can imagine a future millions of years from now, where our descendants live on millions of worlds scattered across our merged local group galaxy. Each world different, each adapted to local conditions, each hosting its own culture and history. Some might be planet-bound, living on terraformed worlds or in sealed habitats. Others might live in vast rotating space stations, building O'Neill cylinders or Bernal spheres. Some might be biological, still recognizably human. Others might be post-biological, having uploaded their consciousness into machines or evolved into forms we can't imagine. This far future humanity might look back at our time and wonder what we were thinking. Why were we worried about reaching other galaxy clusters? We had 1 trillion stars to explore. That's a future worth building toward. Not reaching every galaxy in the universe. That was never possible. But reaching out into our galactic neighborhood, spreading across the Milky Way, building a civilization among the stars of our local group. That is possible. Or at least, it's not ruled out by the laws of physics. Whether it happens depends on us. Let's dig deeper into the expansion of the universe, because understanding this fully helps explain why intergalactic travel is so fundamentally problematic. The expansion of space is not like normal motion. When a car drives away from you, it's moving through space. When a galaxy recedes due to cosmic expansion, it's not moving through space. Space itself is expanding, and the galaxy is being carried along. This distinction matters. If a galaxy were moving through space away from you, you could in principle catch up by going faster. But if space itself is expanding, and the expansion rate is faster than light, at large enough distances, there's no speed through space that allows you to catch up. You're not just chasing a moving target. You're trying to cross an expanding gap where the gap expands faster than you can move. Here's an analogy. Imagine you're on a long rubber sheet that's being stretched uniformly from both ends. You start walking toward a marker on the sheet ahead of you, but the sheet is stretching. As you walk forward, the distance between you and the marker increases because the sheet itself is stretching. If the sheet stretches slowly enough, you can still reach the marker by walking fast enough. But if the sheet stretches faster than you can walk, you'll never reach the marker, no matter how long you walk. You might even find yourself getting farther away, despite walking toward it. That's what's happening with cosmic expansion and distant galaxies. Now, add another wrinkle. The rubber sheet is stretching faster and faster over time. This is the accelerating expansion. Even if you could initially make progress toward the marker, the increasing stretch rate might eventually overcome your walking speed. Suddenly, you're no longer approaching the marker. You're receding from it, despite walking toward it. This is the situation with dark energy. The expansion rate is increasing, which means galaxies that are currently reachable might become unreachable in the future. And galaxies that are already receding faster than light are permanently out of reach. The cosmological event horizon, the boundary beyond which recession velocity exceeds light speed, marks this line of no return. Once a galaxy crosses that boundary, it's gone from our reachable universe forever. We can still see it for a while, because light that left it in the past is still reaching us. But no signal we send now will ever reach it, and no signal it sends now will ever reach us. From our perspective, that galaxy fades away, redshifting toward infinity, eventually becoming invisible. From that galaxy's perspective, we do the same. We become causally disconnected. Two regions of the universe that can no longer influence each other, even in principle. This is a strange kind of barrier. It's not a wall or a force field. There's no physical obstruction. If you traveled toward the horizon, you wouldn't hit anything. You'd just find that you couldn't make progress toward galaxies beyond it. They'd keep receding faster than you could approach. And eventually, as expansion continues, you yourself would find your starting point receding beyond your own horizon. You'd become isolated, unable to return home, unable to reach your destination, stranded in an expanding void. This is why intergalactic travel beyond the local group is not just difficult, but potentially impossible. It's not about building a faster ship. It's about the fundamental structure of space-time, preventing you from closing the distance. Let's consider the energy problem, because even within the local group, reaching another galaxy presents staggering challenges. Accelerating a spacecraft to a significant fraction of light speed requires immense energy. The kinetic energy of an object is 1/2 mass times velocity squared in classical physics. But at relativistic speeds, near the speed of light, you need to use the relativistic formula, and the energy requirements become extreme. To accelerate a 1,000 kilogram spacecraft, about the mass of a small car, to 50% the speed of light requires about 1.1 times 10 to the 20th joules of energy. That's about the total energy output of the sun for several seconds. It's about 200 times the total annual energy consumption of all human civilization. And that's just to accelerate. You also need to decelerate when you arrive, which requires the same amount of energy. So double the energy budget. Now consider that a 1,000 kilogram spacecraft is tiny. It's smaller than any current space probe. Voyager 1 weighs about 725 kilograms. A spacecraft capable of carrying humans, with life support, shielding, and supplies for a million-year journey, would need to be far more massive. Thousands or millions of kilograms. And every additional kilogram multiplies the energy requirement. Where does this energy come from? Chemical rockets won't work. They're far too inefficient. The energy density of chemical fuel is too low. You'd need more fuel than the mass of the spacecraft itself, which then requires more fuel to accelerate that fuel, which requires even more fuel in a vicious cycle. Nuclear propulsion is better. Fission or fusion rockets could provide higher exhaust velocities and better efficiency. But even fusion, which releases roughly 1% of rest mass as energy, might not be enough. To reach 50% light speed, you'd likely need matter-antimatter annihilation, which converts 100% of rest mass to energy. Antimatter rockets are theoretically possible. When matter and antimatter collide, they annihilate, producing pure energy. Use that energy to propel reaction mass, and you have an extremely efficient rocket. But we don't have antimatter. We can produce tiny amounts in particle accelerators, atoms at a time. Scaling up to kilogram or ton quantities is beyond current technology by many orders of magnitude. And storing antimatter is another challenge. It annihilates on contact with normal matter, so you need magnetic containment or some other exotic storage method. Even if you solve the propulsion problem, there's the time problem. Andromeda is 2.5 million light-years away. At 50% light speed, the journey takes 5 million years. From the perspective of travelers experiencing time dilation, it would be less. At 50% light speed, time dilation reduces the experienced time by about 13%, so travelers would experience about 4.3 million years, still far longer than human lifespans. You'd need generation ships, vessels that sustain a population over thousands or millions of years, with many generations living and dying during the voyage. Or you'd need suspended animation, some way to pause biological aging for the duration. Or you'd need to become post-biological, uploading consciousness into machines that don't age. All of this is speculative. We don't know if any of it is possible. And even if it is, there's the navigation problem. Space is not empty. It contains gas, dust, and occasional larger particles. At 50% light speed, even a tiny particle carries enormous kinetic energy. A speck of dust massing 1 milligram hitting your spacecraft at 50% light speed delivers about 4.5 times 10 to the 12th joules, equivalent to more than a ton of TNT. A grain of sand could punch through your hull and destroy your ship. You'd need shielding, but thick shielding adds mass, which increases energy requirements. Or you'd need active deflection systems, magnetic fields or lasers to vaporize or deflect particles in your path. And you'd need to detect those particles far enough ahead to react. At 50% light speed, you cover about 150,000 kilometers per second. If you detect a particle 1 second ahead, you have 1 second to deflect it. If it's closer, you might not have time. And what about larger objects, asteroids, or rogue planets in interstellar space? How do you avoid those? You'd need detailed maps of your route, and you'd need to update those maps constantly as objects move. This is all extraordinarily difficult. Not impossible necessarily, but far beyond anything we can currently do. And that's just for reaching Andromeda, which is within our local group and therefore not subject to the expansion problem. For galaxies beyond our local group, you have all these problems, plus the expansion of space working against you. It's layer upon layer of challenges. Some might be solvable with advanced technology. Others are imposed by fundamental physics and might not be solvable at all. There's also the cosmic ray problem. Cosmic rays are high-energy particles, mostly protons, traveling through space at nearly the speed of light. They're produced by supernovae, black holes, and other high-energy events. Earth's atmosphere and magnetic field protect us from most cosmic rays. But in interstellar space, there's no protection. A spacecraft traveling for millions of years would be bombarded constantly. Crew members would accumulate radiation dose that would be lethal without heavy shielding. And even with shielding, some radiation gets through. Over millions of years, the cumulative damage could be severe. This is yet another engineering challenge. Heavy shielding adds mass, which increases energy requirements. Or you use active shielding, magnetic fields to deflect charged particles. But that requires power, a lot of it, sustained for millions of years. Where does that power come from? Solar panels won't work far from stars. Nuclear reactors could work, but they need fuel, and fuel adds mass. You might use fusion reactors if you can develop them. fusing hydrogen collected from the interstellar medium. But that's speculative technology. Every solution to one problem creates new problems. It's a cascade of challenges. And this is all assuming you have a destination worth reaching. Why go to Andromeda or another galaxy? What's there that's worth a million-year journey? Stars and planets, presumably. But we have stars and planets here. The Milky Way contains hundreds of billions of stars. Most probably have planets. Why leave when there's so much to explore nearby? The only reason to go to another galaxy is if you've already colonized your entire galaxy and need more room. But that would take billions of years. By the time you've colonized the Milky Way, the universe's expansion might have carried all other galaxies beyond reach anyway. You might have missed your window. So the practical answer for any foreseeable future is that intergalactic travel beyond the local group doesn't make sense. It's too hard, too costly, too dangerous, and there's no compelling reason to try when you have a whole galaxy to explore. Now, let's talk about what this means philosophically. Humans have always pushed boundaries. We crossed oceans when we didn't know what was on the other side. We climbed mountains because they were there. We went to the moon not because it was easy, but because it was hard. Exploration is part of human nature. We want to see what's over the horizon, to go where no one has gone before. So, the idea that most of the universe is permanently off limits feels wrong. It goes against our instinct to push farther, to reach beyond our grasp. But the universe doesn't care about our instincts. It operates according to physical laws that don't bend to our desires. And those laws say that the vast majority of galaxies are unreachable. Not unreachable now, with current technology. Unreachable ever, for any technology that obeys known physics. This is a hard truth. It means that our descendants, no matter how advanced they become, will be confined to a small corner of the universe. They can spread across millions or billions of star systems. They can build civilizations that last for cosmological timescales. But they'll do it all within one merged galaxy or galaxy group. Everything beyond that is a view only observable but not visitable. Some see this as a tragedy. The universe is so large, containing trillions of galaxies, and we can only ever reach one tiny part of it. All those other galaxies, all those stars and potential worlds, forever beyond our reach. It's like being shown a vast library containing infinite knowledge, but being told you can only read books in one small section. The rest are there. You can see them on the shelves, but you can never open them. Others see it differently. The accessible universe, our local group, is already almost incomprehensibly large. 1 trillion stars is more than enough for any civilization, no matter how ambitious. We're not trapped in a small cage. We're trapped in a cage the size of 1 trillion suns. And we haven't even begun to explore our own neighborhood yet. We've barely left our own planet. We've sent a handful of probes to the edges of our solar system. We've visited our own moon a few times, decades ago. We haven't set foot on Mars. We haven't even fully explored Earth's oceans. Worrying about being unable to reach distant galaxy clusters seems premature when we can't yet reach the nearest star. So maybe the right perspective is gratitude. We live in a universe rich enough to keep our descendants busy for billions of years. We have a vast cosmic playground within our reach. The fact that we can't reach everything doesn't diminish the enormity of what we can reach. And there's another point worth considering. The unreachability of distant galaxies might actually be good for the universe as a whole. Imagine if faster-than-light travel were easy. Any civilization could zip across the universe, visiting any galaxy they wanted. What happens when civilizations meet? Human history suggests it doesn't always go well. When technologically advanced civilizations encounter less advanced ones, the results are often devastating for the less advanced. Colonization, exploitation, even extinction. Now, scale that to galactic civilizations. An aggressive, expansionist civilization could potentially spread across the entire universe, consuming resources, displacing, or destroying other civilizations. The universe could be dominated by whoever gets a head start and develops the technology first. But with expansion creating barriers, that can't happen. Each galaxy or galaxy group is isolated. Civilizations can rise and fall within their own region without affecting others. The universe becomes compartmentalized. Different regions evolve independently, creating diversity. Instead of one dominant civilization or a few competing ones, you get trillions of isolated pockets, each potentially developing in unique ways. This isolation might be the universe's way of ensuring diversity, a protective mechanism preventing any single civilization or life form from monopolizing everything. Of course, this is speculation. We don't know if other civilizations exist. We've never detected any sign of alien intelligence, despite decades of searching. The Fermi paradox asks why, if the universe is so large and old, we don't see evidence of other civilizations. Where is everybody? One possible answer is that we're alone, the only intelligent life in the universe. Another is that intelligent life is common, but civilizations don't last long. They destroy themselves before spreading beyond their home planet. Another is that faster-than-light travel is impossible, so civilizations are confined to their own stars or galaxies, and we're too far apart to detect each other. The cosmological expansion and the impossibility of intergalactic travel support this last answer. If every civilization is trapped in its own galaxy or galaxy group, and if space between these regions is vast and expanding, then we'd never meet. We could all be out here, scattered across the universe, each building our own civilizations, none aware of the others, because the distances are simply too great. That's a lonely thought, but also a hopeful one. It means we might not be alone, but we're still on our own. No alien saviors coming to solve our problems. No hostile invaders coming to conquer us. Just us, figuring out our future, making our own choices, spreading across the stars if we can, or staying home if we can't. Our fate is in our hands. Let's return to the numbers, because understanding the scale really drives home why this matters. The Milky Way, our home galaxy, is about 100,000 light-years across. It contains 200 to 400 billion stars. Our solar system orbits the galactic center at a distance of about 26,000 light-years, making one full orbit every 225 to 250 million years. The last time we were at this point in our orbit, dinosaurs had just started to appear on Earth. The Milky Way is part of the Local Group, a collection of about 80 galaxies spanning roughly 10 million light-years. The largest members are the Milky Way, Andromeda, and Triangulum. Most of the others are dwarf galaxies, much smaller, containing millions or billions of stars instead of hundreds of billions. The Local Group is gravitationally bound. These galaxies are close enough and massive enough that their mutual gravity overcomes the expansion of space. They're falling toward each other, slowly but inevitably. Over the next several billion years, they'll merge. First, the Milky Way and Andromeda will collide in about 4 billion years. This collision will take billions of years to fully resolve, with the two galaxies passing through each other multiple times before settling into a single elliptical galaxy. Eventually, Triangulum and the dwarf galaxies will merge in as well. The final result, tens of billions of years from now, will be a single large elliptical galaxy containing all the stars from all the original local group members. About 1 trillion stars total. That's our cosmic future. Our accessible universe. 1 trillion stars, countless planets, moons, asteroids. More worlds than we could visit in the entire age of the universe, even if we colonized one new system every year. Beyond the local group, the nearest significant structure is the Virgo cluster. It's about 53 million light-years away and contains over 1,300 galaxies. The Virgo cluster is the gravitational center of the Virgo supercluster, a much larger structure containing about 100 galaxy groups and clusters, including our local group. The Virgo supercluster spans about 110 million light-years. But despite being part of the same supercluster, we're not gravitationally bound to Virgo. The expansion of space is stronger than gravity at this distance. Virgo is receding, and it's already beyond our cosmological event horizon. We can see it, but we can never reach it. Even farther out, the universe is filled with superclusters and voids. Superclusters are massive structures containing many galaxy clusters. Voids are vast, empty regions with few galaxies. Together, they form a cosmic web, a foam-like structure of filaments and voids stretching across the observable universe. The observable universe is about 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies. Each galaxy contains millions, billions, or trillions of stars. The total number of stars in the observable universe is roughly 10 to the 24th power, a 1 followed by 24 zeros. That's more stars than grains of sand on all the beaches on Earth. It's an incomprehensibly large number. And yet, of those 2 trillion galaxies, we can only ever reach a few dozen. The members of our local group, everything else is too far, receding too fast. Less than 100 millionth of 1% of the galaxies in the observable universe are within our reach. That's the scale of our confinement. We can see almost everything, but we can touch almost nothing. It's like being in a vast museum where you can look at the exhibits, but 99.999999% of them are behind glass you can never break. This realization changes how we should think about space exploration. The vision of spreading across the universe, of colonizing countless galaxies, of becoming a truly universal civilization is not possible. We need a more modest, but still grand vision. Spreading across our galaxy, reaching the stars of the local group, building a civilization that spans 1 trillion suns. That's still an almost unimaginably grand project. It would take millions or billions of years. It would require technology we haven't invented yet. It would transform humanity in ways we can't predict. But it's actually possible. It's not forbidden by physics. It's just really, really hard engineering. Compare that to intergalactic travel beyond the local group. That's not just hard engineering. It might be fundamentally impossible. No matter how clever we are, no matter what technology we develop, the expansion of the universe prevents it. So, if we're going to dream about humanity's cosmic future, we should dream about the future that's actually achievable. A future where we've spread across the Milky Way, where millions of human worlds orbit millions of stars, where cultures and civilizations diverse beyond imagining have evolved on different worlds, where humanity, or whatever we've evolved into by then, has filled our galaxy with life and intelligence and creativity. That's a worthy dream. That's a future worth building toward. And it doesn't require violating physics. It just requires surviving, advancing, and having the will to reach for the stars. Our stars. The ones we can actually reach. One more point about the expansion of the universe. The current expansion rate is measured by the Hubble constant, about 70 kilometers per second per megaparsec. But this rate is not constant over time. In the early universe, the expansion rate was higher. As the universe aged and matter density decreased, the expansion slowed. But about 5 billion years ago, something changed. The expansion started accelerating. This is when dark energy became dominant. Before that, matter and radiation were the dominant components, and their gravity was slowing the expansion. But dark energy doesn't dilute as the universe expands. Its density stays roughly constant. So, as the universe grew larger and matter density decreased, dark energy became proportionally more important. Eventually, it dominated, and its repulsive effect started accelerating the expansion. This acceleration is expected to continue indefinitely. As the universe ages, expansion will get faster and faster. More and more galaxies will cross beyond the cosmological event horizon. The observable universe will shrink. Not in the sense that it gets smaller in physical size, but in the sense that fewer and fewer galaxies remain visible and reachable. Eventually, billions of years from now, only our local group will be within our cosmological event horizon. All other galaxies will have receded beyond it. And eventually, even the cosmic microwave background radiation, the afterglow of the Big Bang, will be redshifted to undetectable wavelengths. Future civilizations will live in a universe that appears to contain nothing but their own galaxy, surrounded by darkness. They won't be able to see the cosmic microwave background. They won't be able to observe distant galaxies. They won't have any direct evidence that the universe is larger than their local group. If they develop cosmology and physics, they might be able to infer the existence of a larger universe from theoretical considerations. But they won't have observational evidence. In a way, they'll be in a worse position than we are. We can see 2 trillion galaxies. We can observe the cosmic microwave background. We have direct evidence of the Big Bang and the expansion of the universe. Future civilizations will have none of that. They'll be cosmologically isolated. This is sometimes called the dark era of the universe. As expansion continues, the universe becomes darker, emptier, colder. Star formation will slow and eventually stop as galaxies run out of gas. Stars will age and die, and no new ones will form to replace them. Eventually, the universe will be filled with dead stellar remnants. White dwarfs, neutron stars, black holes. Even those will eventually decay or evaporate over unimaginable timescales. The ultimate fate of the universe is heat death. Maximum entropy, no energy gradients, no structure, no life. But that's trillions of years away. For now, and for the foreseeable future of any civilization we might build, the universe is still rich and dynamic. There are still stars forming, galaxies merging, black holes growing. There's still time. Time to explore, to build, to spread across our galaxy. Time to figure out who we want to be and what kind of future we want to create. The fact that we can't reach every galaxy doesn't change that. We have 1 trillion stars within reach. That's enough. Let's think about what a realistic timeline for human expansion into space might look like. Right now, we're confined to Earth. We've sent people to the moon, but only for brief visits. We have a space station in low Earth orbit, but it's tiny, housing a handful of people. We've sent robotic probes to the planets, but we haven't sent humans beyond the moon. The next step is probably Mars. Multiple space agencies and private companies are working on plans to send humans to Mars, possibly within the next few decades. A Mars mission would be a major milestone, proving that humans can survive extended periods in deep space and on another planet's surface. But Mars is just the beginning. After Mars, we might build permanent bases on the Moon or Mars, then perhaps outposts on moons of Jupiter or Saturn. Europa and Enceladus have subsurface oceans that might harbor life. Titan has a thick atmosphere and surface liquids. These are all within our solar system, reachable with chemical or nuclear rockets within years or decades. Expanding throughout our solar system could take centuries. We'd need to develop technologies for living in space long-term, mining asteroids for resources, building rotating habitats for artificial gravity. We'd need to solve medical problems like muscle atrophy and bone loss in low gravity. We'd need to develop closed-loop life support systems that recycle air, water, and waste. All of this is difficult, but achievable with existing physics. It's engineering, not magic. After we've colonized our solar system, the next step is interstellar travel. The nearest star is Proxima Centauri, about 4.24 light-years away. With current propulsion, a trip there would take tens of thousands of years. But with nuclear pulse propulsion or fusion drives, we might reduce that to hundreds or thousands of years. Still a long time, but not impossible. A generation ship, a vessel designed to sustain a population over many generations, could make the journey. Or we could send frozen embryos and have robots grow and raise the first generation upon arrival. Or we could develop suspended animation technology. Any of these approaches could work, given enough time and development. The first interstellar missions might launch in the next few centuries, if we survive and continue advancing. Early missions would be one way. Send a colony ship to Proxima Centauri or another nearby star. Establish a colony, and that colony becomes independent. No returning home. Over time, we'd send more ships to more stars. Each colony becomes a seed for further expansion. Colonies send out their own ships to other stars, creating a wave of expansion spreading through the galaxy. At an average expansion rate of 1% light speed, colonizing the entire Milky Way would take about 10 million years. That's a long time by human standards, but it's a blink of an eye in cosmic terms. The Milky Way is over 13 billion years old. 10 million years is less than 1% of that. So, it's feasible that a species could colonize an entire galaxy in a small fraction of the galaxy's lifetime. This is part of the Fermi paradox. If life is common, And if technological civilizations naturally expand, then the galaxy should be full of them. We should see evidence everywhere. But we don't. One possible explanation is that civilizations don't expand. Maybe they stay home by choice. Maybe they destroy themselves before expanding. Maybe faster-than-light travel is impossible, so expansion is slow and civilizations are too far apart to encounter each other. Or maybe we're the first. Someone has to be first in the galaxy. Maybe it's us. We don't know. But the point is that expanding across the galaxy is possible in principle. Difficult, slow, requiring technologies we don't have yet. But not impossible. Expanding beyond the galaxy, beyond our local group, is different. That requires dealing with the expansion of the universe. And as we've discussed, that might be insurmountable. So the realistic vision for humanity's future in space is expansion across our solar system over the next few centuries. Then, expansion to nearby stars over the next few thousand years. Then, expansion across the Milky Way over millions of years. And finally, when the Milky Way merges with Andromeda and the local group, expansion across the merged galaxy over tens or hundreds of millions of years. That's a timeline spanning hundreds of millions of years. Far longer than humanity has existed so far. We've only been around as a species for about 300,000 years. Civilization is only about 10,000 years old. Industrial civilization is only a few centuries old. Space age is only decades old. We've barely started. The future we're talking about extends millions of times longer than our past. Who knows what we'll become over that time? We might not even be recognizably human. We might evolve biologically. We might merge with our technology, becoming cyborgs or uploading into machines. We might diverge into multiple species as different colonies adapt to different environments. The humanity of 1 million years from now might be as different from us as we are from Homo erectus. And the humanity of 100 million years from now might be beyond our ability to imagine. But whatever our descendants become, if they exist at all, they'll still be confined to our local group. They'll still be subject to the laws of physics. They'll still live in a universe where most galaxies are forever out of reach. That's the reality we need to accept, not as a limitation that diminishes our potential, but as a boundary that defines the playing field. We have a vast playing field, more than enough room for any conceivable civilization. The challenge is not reaching beyond that field. The challenge is surviving long enough to explore even a fraction of it. Right now, that's not guaranteed. We face existential risks. Climate change, nuclear war, pandemics, asteroid impacts, artificial intelligence risks. Any of these could end our civilization or our species. We've come so far, evolved intelligence and consciousness, developed technology, reached for the stars. It would be tragic to destroy ourselves before we've barely begun. So, maybe the question isn't whether we can reach other galaxies. The question is whether we can survive the next few centuries. Whether we can get through the great filter, whatever that might be. Whether we can make it to the stars at all. If we can do that, if we can survive and expand, then we have a future measured in billions of years and 1 trillion stars. That's the real challenge. Not escaping the Milky Way, but escaping our own self-destructive tendencies. If we can do that, the rest is just engineering and time. Think about what it means to be a biological species trying to comprehend cosmological timescales. Humans live about 80 years on average. Our civilizations last thousands of years. Our species might last hundreds of thousands or millions of years if we're lucky. But the universe operates on timescales of billions of years. Stars live billions of years. Galaxies evolve over billions of years. The universe is almost 14 billion years old and will continue for trillions more. Our existence is a tiny blip in cosmic time. From the universe's perspective, we appeared a moment ago and will be gone a moment from now. This mismatch between human timescales and cosmic timescales makes it hard to think clearly about our place in the universe. We want immediate results, quick progress. But cosmic processes are slow. The merger of the Milky Way and Andromeda will take billions of years. The expansion of the universe is gradual, playing out over billions of years. We're trying to understand and plan for processes that operate on timescales millions of times longer than our lifespans. It's like a mayfly, which lives for a single day, trying to understand the changing of the seasons. The mayfly doesn't live long enough to experience summer and winter. It can't directly observe the cycle. It would need to piece together the pattern from indirect evidence and from information passed down by previous generations of mayflies. We're in a similar position with cosmic timescales. We can observe and measure and theorize, but we can't directly experience billions of years. We have to extrapolate, using physics and mathematics to project forward and backward across timescales we'll never personally witness. And yet, we do it. We figure out the age of the universe, the life cycle of stars, the fate of galaxies. We predict what will happen billions of years from now, with reasonable confidence. That's an extraordinary achievement. It's one of the defining characteristics of intelligence. The ability to think beyond immediate experience, to understand processes operating on timescales far longer than individual lifespans. No other species on Earth can do this. Other animals live entirely in the present, or perhaps in the very recent past and immediate future. They don't contemplate the distant past or far future. They don't wonder about their place in the cosmos. We do. And that's special. It doesn't make us cosmically important. The universe doesn't care about us. But it makes us interesting, at least to ourselves. We're matter that has become aware of itself, that can study its own origins, that can predict its own future. We're the universe's way of understanding itself, if only in a tiny corner of space and time. That's worth something. Even if we're trapped in the Milky Way, even if we can never reach the vast majority of galaxies, we can still observe them. We can still study them. We can still understand them. We can still appreciate the beauty and complexity of the universe. That's a form of exploration, even if it's not physical travel. Our telescopes carry us across the cosmos, gathering light from billions of light years away, showing us galaxies as they were billions of years ago. We can see the universe's history. We can map its structure. We can understand its evolution. We're not just passive inhabitants of the universe. We're active observers, participants in the cosmic story. And that remains true whether or not we ever leave our galaxy. So yes, we may never leave the Milky Way. The expansion of the universe makes intergalactic travel beyond our local group essentially impossible with known physics. But that's okay. We have enough universe to explore right here. 1 trillion stars, countless worlds, billions of years ahead of us if we survive. The real question is not whether we can escape our cosmic cage. The real question is what we do with the vast space we have available. Do we fill it with life and intelligence and creativity? Do we build a civilization worth having? Do we survive long enough to reach even a tiny fraction of our potential? Those are the questions that matter, not whether we can visit the Andromeda galaxy or the Virgo cluster. Those are beautiful to observe, fascinating to study, but ultimately not necessary for our future. Our future is here, in the Milky Way, among the stars we can actually reach. And that's more than enough. Let me take you deeper into what dark energy actually is, because understanding this mysterious force helps explain why our cosmic confinement is so absolute. Dark energy was discovered by accident in 1998. Two teams of astronomers were studying distant supernovae, trying to measure how much the universe's expansion was slowing down. Everyone expected to find deceleration. After all, gravity pulls everything together, so the expansion left over from the Big Bang should be gradually slowing, like a ball thrown upward, eventually falling back down. The teams looked at Type Ia supernovae, extremely bright stellar explosions that can be seen across billions of light years. These supernovae are useful because they're standard candles, explosions that always reach roughly the same peak brightness. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. By measuring both distance and recession velocity for many distant supernovae, the teams expected to plot a curve showing expansion gradually decelerating over cosmic time. Instead, they found the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than expected for their recession velocity. The universe wasn't decelerating. It was accelerating. Expansion was getting faster over time, not slower. This was completely unexpected. It required something pushing space apart, counteracting gravity, causing acceleration. They called it dark energy because we can't see it and we don't know what it is. We only know it's there because of its effects. The simplest explanation for dark energy is the cosmological constant, an idea Einstein originally proposed and then abandoned. In 1917, Einstein was developing general relativity and applying it to the universe as a whole. His equations predicted that the universe should either be expanding or contracting. It couldn't be static. But at the time, astronomers believed the universe was static, unchanging. So Einstein added a term to his equations, the cosmological constant, a kind of repulsive gravity that could balance normal gravity and keep the universe static. Then, in the 1920s, Edwin Hubble discovered that the universe actually is expanding. Galaxies are moving apart. Einstein realized his cosmological constant was unnecessary and called it his biggest blunder. But now, it's back. If the cosmological constant exists and has the right value, it produces exactly the kind of acceleration we observe. It acts like a property of space itself. As space expands, more space is created, and each volume of space contributes the same amount of dark energy. So, as the universe grows, the total amount of dark energy increases. Meanwhile, the matter density decreases as the same amount of matter spreads through ever larger volume. Eventually, dark energy dominates, and its repulsive effect causes acceleration. This matches what we observe. But we don't know why the cosmological constant has the value it does. Quantum field theory predicts there should be a cosmological constant arising from vacuum energy, the energy of empty space due to quantum fluctuations. But the predicted value is about 10 to the 120th power times larger than what we observe. That's 1, followed by 120 zeros. It's the worst prediction in the history of physics, off by 120 orders of magnitude. Something is cancelling out almost all of that vacuum energy, leaving only a tiny residual amount that acts as dark energy. We don't know what or why. This is one of the deepest unsolved problems in fundamental physics. It's called the cosmological constant problem. There are alternative theories where dark energy isn't a constant but varies over time or space. These are called quintessence models, after the ancient idea of a fifth element beyond earth, air, fire, and water. In quintessence models, dark energy is a dynamic field that changes as the universe evolves. Maybe it's getting stronger, which would make expansion accelerate even faster. Maybe it's getting weaker, which could eventually allow gravity to take over again. We don't know. Current observations are consistent with a cosmological constant, but they don't rule out quintessence. We need more precise measurements to distinguish between the models. Whatever dark energy is, its effect is clear. It's pushing the universe apart, faster and faster. And this has profound implications for the future. Not just for intergalactic travel, but for the ultimate fate of everything. If dark energy remains constant or gets stronger, the universe will continue accelerating forever. Expansion will get faster and faster with no limit. Eventually, the acceleration becomes so extreme that it tears apart structures. First, galaxy clusters unbind, then individual galaxies, then solar systems, then planets. Eventually, even atoms themselves get ripped apart. This is called the Big Rip, one possible fate of the universe if dark energy is much stronger than current measurements suggest. Current data doesn't support the Big Rip scenario. Dark energy seems to be just strong enough to cause acceleration, but not strong enough to tear everything apart. The more likely fate is heat death. Galaxies continue to recede. Structure formation slows and stops. Star formation uses up available gas. Stars age and die. Eventually, the universe is filled with stellar remnants, black holes, and diffuse radiation. Everything reaches maximum entropy. No energy gradients remain to power any processes. The universe becomes dark, cold, and dead. This takes an incomprehensibly long time. Stars will continue forming for perhaps another trillion years. The longest-lived stars, small red dwarfs, can burn for tens of trillions of years. Even after the last stars die, stellar remnants like white dwarfs remain, slowly cooling over quadrillions of years. Black holes evaporate through Hawking radiation, but this takes unimaginable timescales. A solar mass black hole takes about 10 to the 67th years to evaporate. A supermassive black hole can take 10 to the 100th years or longer. By the time the universe reaches true heat death, the current age of the universe, 14 billion years, will seem like the blink of an eye. We're living in the very early universe, the brief era when stars shine and galaxies shine and life is possible. Most of the universe's future is darkness and decay. But again, that's trillions of years away. For any foreseeable future, the universe is still vibrant. And for any civilization that might arise, the local group provides more than enough space and resources. The dark energy problem connects to another mystery, dark matter. Dark matter is different from dark energy. Dark matter is matter we can't see. That makes up about 27% of the universe's total mass energy. We know it exists because we can see its gravitational effects. Galaxies rotate too fast. The stars in the outer parts of galaxies are moving so quickly that they should fly off into space unless there's more mass holding them in than we can see. That unseen mass is dark matter. Galaxy clusters contain more mass than we can account for from visible stars and gas. The extra mass is dark matter. Gravitational lensing, the bending of light by gravity, shows that massive objects bend light more than their visible mass would predict. The extra lensing is caused by dark matter. The cosmic microwave background, the afterglow of the Big Bang, has patterns that only make sense if dark matter exists. So, we're confident dark matter is real, but we don't know what it is. It doesn't emit, absorb, or reflect light. It only interacts through gravity. The leading candidate is some new type of particle that doesn't interact electromagnetically, only gravitationally, and perhaps weakly through other forces. Physicists have built detectors deep underground to search for these particles. So far, they haven't found them. But the search continues. Dark matter and dark energy together make up about 95% of the universe. Only 5% is normal matter, the stuff we're made of, the stuff that makes up stars and planets and everything we can see. We're the minority component of the universe. Most of what exists is dark, invisible, and mysterious. This is humbling. We've figured out so much about the universe. We've measured its age, mapped its structure, traced its evolution from the Big Bang to now. But we still don't know what most of it is made of. We're like someone who's carefully mapped the surface of an ocean, but has no idea what's in the depths below. The surface is only a tiny fraction of the total. Most of the ocean is dark, unexplored mystery. We're in a similar position with the universe. We've mapped the visible, the normal matter. But the bulk of reality is dark matter and dark energy, and we don't understand either. This is one of the great challenges for 21st century physics. Figure out what dark matter and dark energy are. Understand why the cosmological constant has the value it does. Develop a theory that unifies gravity with quantum mechanics. These are hard problems. They might take decades or centuries to solve. Or they might never be solved fully. We might reach limits of what's knowable. Some questions might not have answers accessible to beings like us with our limitations. But we keep trying. That's what science is. Asking questions, testing ideas, gradually expanding the boundary of knowledge. Sometimes, the answers create new questions. Dark energy is a perfect example. We discovered it, measured it, but we don't understand it. And now it raises all these new questions about the universe's fate and the nature of space, and whether fundamental physics is incomplete. We've opened a door, but behind it is a bigger mystery than we expected. That's both frustrating and exciting. It means there's still so much to learn. Let's talk about the practical implications of cosmic expansion for navigation. If you're trying to travel to a distant galaxy, you can't just point your ship at where the galaxy is now and start flying. By the time you arrive, the galaxy will have moved. And not just moved through space, but been carried away by expansion. You need to aim at where the galaxy will be when you arrive. But calculating that requires knowing the expansion rate, the galaxy's current distance and velocity, and how both will change over the millions of years of your journey. For galaxies within the local group, this is manageable. Expansion is negligible at these distances. Gravity dominates. You can use standard orbital mechanics to plot a course. It's complicated, but not impossible. For galaxies beyond the local group, it becomes problematic. You're trying to hit a moving target where the target is accelerating away from you. It's like trying to throw a ball to someone who's on a train that's speeding up. By the time the ball gets to where they were, they've moved farther down the track. You have to lead the target, but the target is accelerating, so you have to account for that too. And if the train is accelerating fast enough, there's no way to throw the ball hard enough to catch up. That's the situation with distant galaxies. They're receding and accelerating. At some distance, no trajectory exists that would allow you to reach them. You could fly directly at them at light speed, and you'd still fall farther behind every year. This is profoundly different from any navigation problem we face on Earth or in our solar system. On Earth, if you want to reach a destination, you point yourself at it and start moving. You might need to account for wind or currents, but the destination isn't running away from you. In our solar system, objects move in predictable orbits. You can calculate where a planet will be and plot an intercept course. NASA does this routinely. The Voyager spacecraft were launched to intercept Jupiter and Saturn, arriving exactly when and where predicted. But with distant galaxies, the destination is literally unreachable, not because you can't calculate the course, but because no course exists. It's not a navigation problem. It's a fundamental impossibility. Even if you had perfect information and perfect control, you can't overcome the expansion of space. This is hard for our brains to accept. We're used to the idea that, with enough effort, any destination can be reached. Climb high enough, and you reach the mountain summit. Sail far enough, and you cross the ocean. Fly fast enough, and you can go anywhere on Earth. But the universe doesn't work that way. Some destinations are unreachable, not temporarily, not until we develop better technology, but permanently, for all time. It's a hard limit, imposed by the structure of reality itself. Now, let's consider what life might be like for a civilization that's fully accepted this limitation and built their society around it. Imagine humans, millions of years in the future. We've spread across thousands of star systems in the Milky Way. Each system is home to billions of people living on planets, moons, and artificial habitats. The total human population is in the trillions or quadrillions. Cultures have diverged enormously. Each star system has developed its own languages, customs, traditions. Some systems are connected by trade and communication, forming alliances or confederations. Others are isolated, having lost contact or chosen independence. The distances between stars mean that communication is slow. Even at light speed, messages take years to travel between nearby stars and decades or centuries to cross larger distances. There's no faster-than-light communication, no subspace radio or Ansible, just light, carrying information at its maximum speed. This means no central government can control a galactic civilization. By the time orders reach a distant colony and a response returns, decades or centuries have passed. The situation has changed. The orders are obsolete. Local autonomy is inevitable. Each system governs itself, makes its own decisions, deals with its own problems. The best you can have is a loose confederation of independent systems that share culture, history, and perhaps trade, but not governance. Think of it like Earth's history, when communication was slow. Ancient Rome couldn't micromanage distant provinces. Messages took weeks or months to travel by ship or horseback. Provincial governors had broad autonomy because the central government couldn't respond quickly to local situations. Similarly, a galactic civilization can't have a central authority. It's physically impossible. The light speed limit for communication ensures that. This might actually be good. It prevents tyranny on a galactic scale. No dictator can rule the entire galaxy when they can't communicate with most of it in their lifetime. No empire can enforce its will across thousands of light years when rebellions can happen and be resolved before news of them reaches the capital. Decentralization is enforced by physics. Each system is free to experiment, to try different forms of government, different social structures, different philosophies. Over millions of years, this produces incredible diversity. Some systems might remain democratic. Others might develop into monarchies, technocracies, collective hives, or forms of organization we haven't thought of. Some might enhance themselves biologically, using genetic engineering to adapt to local conditions. Others might merge with technology, becoming cyborgs or uploaded minds. Some might stay close to baseline human. Others might become so different they're unrecognizable. And all of this is within one galaxy, within reach, accessible even if the journeys take years or decades. Now imagine trying to extend this to other galaxies. Even if you could reach Andromeda, the round-trip communication time would be 5 million years. You send a message to an Andromeda colony. 5 million years later, you receive a reply. By then, civilizations have risen and fallen. Languages have evolved beyond recognition. The original message might be in a dead language that the recipients have to decipher like archaeologists. The society that sent the message no longer exists. The society that receives it might not care about a 5 million-year-old message from a distant ancestor civilization. It's not meaningful communication. It's more like archaeology, finding messages from a lost ancient society. This is why intergalactic civilization doesn't make sense, even if travel were possible. The distances and timescales are too large for any form of cohesive society. You'd have isolated pockets that diverge completely, never interacting in any meaningful way. At that point, what's the purpose? You're not building a civilization. You're seeding completely independent civilizations that will never communicate. They share a common origin, but they're not connected. It's the same outcome as if they evolved independently. So even without the expansion problem, intergalactic civilization is questionable. But with the expansion problem, it's impossible. You can't even seed those independent civilizations because you can't reach the other galaxies in the first place. The universe has effectively compartmentalized itself. Each galaxy or galaxy group is a separate domain, isolated from the others. Within each domain, civilizations can rise, spread, diversify, but they can't cross to other domains. This might be the universe's way of ensuring diversity on the largest scales. If all galaxies were easily reachable, one successful civilization might spread everywhere, homogenizing the universe. But with isolation, each galaxy can develop its own unique story. Different life forms, different civilizations, different paths. The universe becomes a patchwork of isolated experiments, each running independently. We'll never know what's happening in other galaxies. We can observe them, see their light, study their structures. But we can't visit them, can't meet whatever civilizations might exist there, can't share our stories or learn theirs. Each galaxy is a separate book in a library where the books can't be removed from the shelves. We can look at the covers, read the titles, maybe catch glimpses of a few pages. But we can't read the full stories. We're confined to our own book, our own galaxy, our own story. And that story, if we write it well, can be extraordinary on its own. Let's explore some of the specific engineering challenges of interstellar travel within our galaxy. Because even though it's theoretically possible, it's extraordinarily difficult. One of the biggest problems is energy. We've talked about this, but let's get more specific. A spacecraft needs energy for acceleration, for life support, for station keeping, for communication, for all its systems. Where does this energy come from? Chemical rockets are out. The energy density is too low. You'd need impossibly large fuel tanks. Nuclear fission could work for slow interstellar probes. The Voyager spacecraft use radioisotope thermoelectric generators powered by decaying plutonium. These produce a few hundred watts of power, enough for instruments and communication. But they're not propulsion systems. They're just power sources. For propulsion, you need something much more powerful. Nuclear pulse propulsion is one option. This is the Orion project concept from the 1950s. You drop nuclear bombs behind your spacecraft and ride the shockwave. Each bomb gives you a push. Drop enough bombs and you accelerate to a significant fraction of light speed. The engineering is brutal. You need a massive shock absorber to protect the crew from the acceleration. You need thousands or millions of nuclear devices. You need to make sure the bombs explode at exactly the right positions and times. And you're flying through space in a ship being repeatedly hit by nuclear explosions. It's insane, but the physics works. Calculations suggest you could reach about 10% light speed with a nuclear pulse drive. That would get you to the nearest star in about 42 years. Still a long time, but manageable within a human lifetime. The problem is that no one wants to build a ship powered by nuclear bombs. It's politically unpalatable. And the engineering challenges are enormous. Nuclear fusion is more attractive. Fuse hydrogen into helium, like the sun does, and use the energy for propulsion. Fusion produces much more energy per unit mass than fission. And hydrogen is the most abundant element in the universe. You could potentially scoop up interstellar hydrogen as you fly, refueling as you go. This is the Bussard ramjet concept. A giant scoop collects hydrogen from space, fuses it, and uses the energy for thrust. In theory, you could accelerate indefinitely, reaching speeds very close to light speed. The problem is that interstellar space is very empty. The hydrogen density is only about 1 atom per cubic centimeter. That's an incredible vacuum by Earth standards. To collect meaningful amounts, your scoop would need to be enormous, thousands of kilometers across. And the faster you go, the more drag you experience from hitting even that tenuous gas. At some point, drag equals thrust, and you can't accelerate anymore. Current calculations suggest a Bussard ramjet might not actually work as originally envisioned. But variants might. Using the collected hydrogen for fuel, but not relying solely on fusion thrust. Antimatter is the ultimate rocket fuel. When matter and antimatter meet, they annihilate completely, converting 100% of mass to energy. That's the theoretical maximum efficiency. E equals mc squared. A tiny amount of antimatter could power a spacecraft to relativistic speeds. 1 kilogram of antimatter annihilating, with 1 kilogram of matter releases, about 1.8 times 10 to the 17th joules. That's roughly the energy of the largest thermonuclear bombs ever tested. Use that energy efficiently, and you could accelerate a ship to a significant fraction of light speed. The problems are producing and storing antimatter. We can make antimatter in particle accelerators, but only in microscopic amounts. A few atoms at a time. Scaling up to kilograms is beyond current technology by many orders of magnitude. And antimatter annihilates on contact with normal matter, so you can't store it in a normal container. You need magnetic bottles or some other exotic storage method. If the containment fails, all your antimatter annihilates instantly, destroying your ship. It's extremely dangerous. But if we solve these problems, antimatter rockets could make interstellar travel practical. Another approach is beam propulsion. Instead of carrying your fuel with you, you get energy beamed to you from a laser or particle beam. A giant laser array in orbit around the Sun focuses a beam on your spacecraft's light sail. The photon pressure accelerates you. The advantage is that your spacecraft doesn't need to carry fuel. It can be much lighter. The disadvantage is that you need an enormous laser array, and you're limited to routes where the beam can reach you. Once you're too far away or blocked by something, the beam can't accelerate you anymore. But for the initial acceleration phase, beam propulsion could work. You could accelerate a small probe to 20 or 30% light speed. At that speed, you'd reach Proxima Centauri in about 15 to 20 years. That's fast enough to get data back within a human lifetime. This is the concept behind Breakthrough Starshot, a project proposed to send tiny probe to Alpha Centauri using laser-pushed light sails. The probes would be gram-scale, weighing only a few grams, with a light sail several meters across. A powerful laser array on Earth or in space would blast them with light, accelerating them to 20% light speed in minutes. The challenge is keeping the laser focused on such a tiny target as it recedes. And the probes are so small, they can only carry minimal instruments. But it's a start. If we can do this, we prove that interstellar travel is possible, even if only for tiny, unmanned probes. After that, we can work on scaling up. Larger probes, eventually crewed missions, using more powerful propulsion systems. It's a pathway from where we are now to where we need to be. The other major challenge is life support. Humans need air, water, food, protection from radiation, artificial gravity to prevent muscle and bone loss. For a trip lasting years or decades, you need a closed-loop system that recycles everything. Water can be recycled through filtration and purification. The International Space Station does this now. Astronauts drink water that's been recycled from sweat, urine, and humidity in the air. It sounds gross, but it's clean, safe, and necessary. Air is harder. You need to remove carbon dioxide and replenish oxygen. Plants can help with this, photosynthesizing to produce oxygen and absorb carbon dioxide. But you need a lot of plants and they need light and nutrients. A spacecraft would need greenhouses or farming modules. Food is another challenge. You can't carry enough for decades or centuries. You need to grow it. Hydroponics, aeroponics, or some other method to produce vegetables, grains, maybe even meat through cell cultures. This requires space, energy, and expertise. Your crew needs to include farmers, engineers, doctors, all the specialties necessary to keep the ship running and the crew alive. For a generation ship, a vessel that sustains a population over many generations, you need even more. You need genetic diversity to avoid inbreeding. That means a population of at least a few hundred people, maybe 1,000. You need social structures, governance, education, culture. The ship becomes a small society, a flying city. People are born on the ship, live their entire lives there, and die without ever reaching the destination. Only their descendants will arrive. This requires a sense of purpose, a shared mission that can sustain commitment across generations. It's not just engineering. It's social, psychological, cultural. Can a society maintain focus on a goal that won't be achieved for hundreds of years? Can they avoid conflicts that tear the society apart? Can they maintain the knowledge and skills necessary to operate the ship and establish a colony upon arrival? These are open questions. We don't know if generation ships are psychologically feasible. They've never been tried. It's possible that the first few generations would stay committed, but later generations might lose interest, might turn the ship around, might split into factions. Or they might thrive, building a unique culture adapted to life in space, and they might successfully establish colonies on distant worlds. We won't know until we try, and we're a long way from trying. We've barely established a permanent presence in low Earth orbit. We haven't even built a self-sustaining base on the Moon or Mars. Generation ships to other stars are centuries away at minimum, but they're not impossible. They're just hard. Really, really hard. Let me address one more common question. What about wormholes or warp drives? Haven't we talked about these? But let's be clear about what they require. Wormholes are solutions to Einstein's equations that connect two distant points in space through a shortcut. Think of space like a folded piece of paper. 2 points on opposite sides of the paper are far apart if you travel across the surface. But if you poke a hole through both layers, you create a shortcut. That's a wormhole. The mathematics works. General relativity allows these solutions. But creating and stabilizing a wormhole requires exotic matter with negative energy density. This is matter that has less than zero energy. Quantum field theory allows for tiny, temporary regions of negative energy through something called the Casimir effect. If you place two metal plates very close together in a vacuum, quantum fluctuations between the plates are restricted compared to outside. This creates a tiny negative energy pressure that pushes the plates together. It's been measured in labs. But the amount is minuscule, and it only exists in that specific configuration. Scaling it up to macroscopic amounts sufficient to hold open a wormhole is purely speculative. We don't know if it's possible. Even if you could create exotic matter, you face other problems. Wormholes are unstable. Anything passing through would perturb the throat, potentially causing it to collapse. You'd need active stabilization, constantly adjusting the exotic matter to keep the wormhole open. And there are causality issues. Some wormhole configurations allow closed time-like curves, paths through space-time that loop back on themselves. That means time travel into the past, which creates paradoxes. Many physicists believe that some unknown law of physics prevents this, maybe a cosmic censorship that forbids wormhole configurations that allow time travel. But we don't know. We don't have a complete theory of quantum gravity, and that's what you'd need to fully understand wormholes. The Alcubierre drive is another theoretical possibility. This is a solution where you create a bubble of space-time around your ship. You contract space in front of you and expand it behind you. The bubble moves faster than light, but locally, inside the bubble, you're not moving at all. You're standing still while space moves around you. This doesn't violate relativity because nothing is moving through space faster than light. Space itself is moving. Again, the mathematics works. The problem is that creating the bubble requires huge amounts of negative energy distributed in a specific configuration around your ship. Original calculations suggested you'd need negative energy equivalent to the mass of Jupiter or even more. Later refinements reduced this, but it's still astronomical. And you have the same problem as with wormholes. We don't know if negative energy in these amounts can exist or be controlled. There are also practical problems. You can't steer while inside the bubble. You can't turn it on or off from inside. You'd need infrastructure at both your starting point and destination to create and collapse the bubble. That means someone has to go there first, conventionally, to set up the equipment. So, warp drives don't help you reach new places. They only help you travel between places you've already connected. And finally, there might be fundamental reasons why these exotic solutions can't actually work. Some physicists argue that quantum effects would destroy any wormhole or warp bubble before it could be used. Radiation would build up to infinite density, causing a feedback loop that collapses the structure. Others argue that the energy conditions required violate principles we haven't discovered yet. The point is, these are highly speculative. They're fun to think about, and they make great science fiction. But betting humanity's future on them would be unwise. We should assume that faster-than-light travel is impossible and plan accordingly. If it turns out to be possible after all, that's a wonderful surprise. But we shouldn't count on it. So, where does this leave us? We've explored the science, the engineering, the physics. We've looked at the expansion of the universe, dark energy, the limitations on travel, the challenges of life support and propulsion. We've considered what it means to be confined to our galaxy. The conclusion is clear. Intergalactic travel beyond our local group is almost certainly impossible with any technology consistent with known physics. The expansion of the universe creates barriers that cannot be crossed. Dark energy is accelerating this expansion, making it worse over time. More and more galaxies are crossing beyond our cosmological event horizon, becoming forever unreachable. We might spread throughout the Milky Way. We might reach Andromeda and the other members of our local group. But that's it. That's our cosmic future. 1 trillion stars. Countless worlds. Billions of years of potential history. It's not unlimited, but it's vast, beyond our current ability to explore or even imagine. The question for humanity is whether we'll survive long enough to even begin this journey. Right now, we're confined to one small planet. we face existential risks: climate change, nuclear weapons, pandemics, artificial intelligence, asteroid impacts. Any of these could end us before we ever leave our solar system. If we can get through the next few centuries without destroying ourselves, we might have a future among the stars. We might become a species that spans solar systems, that builds habitats in space, that transforms other worlds. We might become the first successful spacefaring civilization from Earth, spreading life and intelligence throughout our region of the galaxy. And if we do that, if we achieve even a fraction of this potential, the fact that we can't reach other galaxy clusters won't matter. We'll have more than enough universe to call home. So, yes, we may never leave the Milky Way, but the Milky Way is enough. It's a galaxy of wonders, hundreds of billions of stars, each one a sun, each potentially hosting worlds. The challenge isn't escaping our galaxy. The challenge is surviving, advancing, reaching for the stars we can actually touch, and building a future worthy of the cosmic opportunity we've been given. Thanks for staying with me through this long journey across the cosmos and through the limits imposed by its expansion. The real reason we may never leave the Milky Way isn't technology or willpower. It's the fundamental structure of space-time itself, the accelerating expansion driven by dark energy, creating barriers that no amount of advancement can overcome. But within our reach, we have 1 trillion suns waiting, a cosmic playground vast beyond comprehension. The question isn't whether we can escape. The question is whether we'll survive and thrive in the extraordinary galaxy we already call home. One more practical consideration about expansion throughout the galaxy. Even within the Milky Way, communication would be challenging. The galaxy is 100,000 light-years across. A message from one side to the other takes 100,000 years. That's longer than recorded human history. By the time a reply comes back, 200,000 years have passed. Civilizations rise and fall in that time. Languages change beyond recognition. Technology advances or regresses. The people who sent the original message are long dead, their civilizations possibly vanished. So in practice, even within our galaxy, different regions would be largely independent. You might have zones of local communication, clusters of nearby stars that can talk to each other with delays of years or decades rather than millennia. But galaxy-wide coordination would be impossible. Any galactic civilization would be more like a loose association of independent regions rather than a unified government. Think of it like human history on Earth before modern communication. Different continents developed independently for thousands of years. When they finally made contact, they were completely different civilizations with different languages, technologies, and cultures. The Aztecs and the Spanish, meeting in 1519, were both human societies that had diverged thousands of years earlier. They could barely communicate, had completely different worldviews, and the contact was catastrophic for one of them. Now, scale that up to galactic distances. Different star systems, separated by hundreds or thousands of light years, developing independently for tens of thousands or millions of years. By the time they make contact, they might have diverged so much they're incompatible. Different biologies, if they've adapted to different environments. Different psychologies, if they've evolved or engineered themselves in different directions. Different values, priorities, goals. Contact might be fascinating, leading to exchange of ideas and culture, or it might be disastrous, leading to conflict or simply mutual incomprehension. we don't know. We've never been in that situation. All of human history has taken place on one planet with one species. We've never encountered another intelligent species. We've never had to navigate the complexities of truly alien contact. But if we spread across the galaxy, our descendants will face this. They'll encounter other human-descended civilizations that have diverged so much they might as well be alien. How will they react? With curiosity and openness? With suspicion and hostility? With indifference? These are questions we can't answer now, but they're worth thinking about because they'll shape the future. A galaxy full of diverse, independent civilizations could be a rich tapestry of different cultures and ideas. Or it could be a battleground of competing factions. Or it could be a collection of isolated groups that rarely interact. The path we choose now, the values we instill in our culture, might influence which future we get. If we build a civilization based on cooperation, respect for diversity, and peaceful coexistence, our descendants might carry those values forward. If we build a civilization based on competition, domination, and conflict, that might be the legacy we pass on. Culture persists. Values endure, even as societies change. The choices we make now echo into the future. This is both a responsibility and an opportunity. We're not just living our lives. We're shaping the foundation of something that might last millions of years. Our art, our literature, our philosophy, our scientific discoveries, all of it becomes part of the cultural DNA that our descendants inherit. They'll build on it, modify it, sometimes reject it, but it will influence them. Just as we've been influenced by ancient civilizations that came before us. We still read ancient Greek philosophy, study ancient Egyptian engineering, appreciate ancient Chinese art. Those civilizations are gone, but their influence persists. Our civilization might influence the galaxy in the same way. Long after we're gone, long after Earth is a distant memory, our ideas and values might still be shaping societies on distant worlds. That's a form of immortality, not personal, but cultural. The things we create, the knowledge we discover, the values we uphold, outliving us by millions of years. It's a profound responsibility, but it's also deeply meaningful. What we do matters, not just for us, not just for our children, but potentially for countless generations yet unborn, living on worlds we'll never see, under stars we'll never visit. Let's bring this back to Earth, to the present moment. We've spent all this time talking about the far future, about galaxies and dark energy and cosmic expansion. But what does any of this mean for us right now? Why does it matter that we can't leave the Milky Way when we can't even leave Earth in any significant numbers? It matters because it shapes how we think about our place in the universe. It matters because it helps us understand the scope and limits of our cosmic future. It matters because it focuses our attention on what's actually achievable rather than impossible dreams. We live in a time when space travel is transitioning from government programs to private enterprise. Companies are building reusable rockets, planning missions to Mars, talking about space tourism and asteroid mining. There's renewed enthusiasm for space exploration after decades of relative stagnation. This is exciting. It's the beginning of something important. But we need to be realistic about what's possible and what's not. Reaching Mars is hard but achievable. Establishing a self-sustaining colony on Mars is harder, but still possible. Spreading throughout our solar system, mining asteroids, building habitats in space, all of this is difficult, but within the realm of possibility. Reaching nearby stars is much harder, but not impossible. It will require technologies we haven't developed yet, but nothing that violates known physics. Reaching Andromeda is even harder, requiring million-year journeys, but it's still technically possible. Reaching the Virgo cluster or other distant galaxies is almost certainly impossible. The expansion of the universe prevents it. Understanding these distinctions helps us set realistic goals. We should invest in technologies that enable solar system exploration and eventual interstellar travel to nearby stars. We shouldn't waste resources chasing impossible dreams of intergalactic travel to distant galaxy clusters. This doesn't mean we stop exploring. It means we explore intelligently, working on challenges that can actually be solved. And there are plenty of those challenges to keep us busy for centuries. How do we build sustainable habitats on Mars? How do we mine asteroids economically? How do we protect astronauts from radiation during long-duration missions? How do we develop propulsion systems capable of reaching nearby stars? How do we create closed-loop life support systems for generation ships? These are all hard problems. Solving any one of them would be a major achievement. Solving all of them would enable humanity to spread beyond Earth, to become a true spacefaring civilization. And that's the goal we should focus on. Not escaping the Milky Way, but escaping Earth's cradle, reaching for the nearby stars, building a future among the cosmos. It's an achievable goal if we commit to it. If we invest the resources, develop the technology, foster the international cooperation necessary to make it happen. It won't happen quickly. It will take generations. But it's possible, and it's worth doing. Because the alternative is staying on Earth forever, putting all our eggs in one basket, risking extinction from any number of threats. Asteroid impact, supervolcano eruption, pandemic, nuclear war, climate catastrophe. Any of these could devastate Earth's biosphere. If we're confined to one planet, we're vulnerable. But if we've spread to multiple worlds, to habitats throughout the solar system, eventually to other star systems, then we're resilient. No single catastrophe can end us. That's the practical reason for space exploration. Not grand dreams of galactic empires. Simple survival, making sure humanity has a future beyond this one fragile world. And there's another reason, less practical but equally important. Wonder, curiosity, the desire to explore and discover. These are fundamental parts of being human. We've always wanted to know what's over the horizon, what's beyond the mountains, what's across the sea. Now the frontier is space. The stars beckoning us, calling us to explore. We may never reach most of them. The universe may be forever beyond our grasp, except for our small corner. But that corner is still vast and full of wonders. And the journey to explore it, to spread throughout our galaxy, to see what's out there, will be one of the great adventures in human history, perhaps the greatest. So yes, we may never leave the Milky Way. The expansion of the universe, driven by dark energy, creates barriers we cannot cross. The vast majority of galaxies are forever out of reach. But we have our galaxy, our local group, 1 trillion stars and countless worlds. We have enough universe to explore for billions of years. And the question is not whether we can have everything. The question is whether we'll make the most of what we have. We're at a turning point. We can destroy ourselves, or we can reach for the stars. The choice is ours. Let's choose to survive, to explore, to build something lasting. Let's create a civilization that future generations will look back on with pride. And if we do it well, the Milky Way will be more than enough. It will be home, adventure, and legacy, all in one. 1 trillion stars waiting for us. That's our cosmic inheritance.